Okay, so welcome to the last session. I'm saying last because I'll be doing a 1 hour recap through of the kind of concepts that we have seen uh, by solving some problems. Okay. So this is optimization from fundamentals. Yeah, so I'll just get started with the problems right away. We look at a question of line search, exact line search. Okay. So we'll keep it simple. We'll take the functions to be objective function to be quadratic. Right, and what is exact line search? Okay, so the idea is that given any direction d, actually it will be physical direction, but right now I'm just writing direction d, we want to solve okay, so I'm at a point x, and I have, for some due to various reasons, I think that d is the direction in which I should be moving to minimize my objective function. Point is, I want to know what should be the step size along that direction. How far along that direction should I move? So it will be great if ideally I would want to do this exact line search. Of course, in practice it's often not possible, but here, because it's a quadratic function, you will soon see that we can do that. But so let's just go ahead and do the algebra and see when we cannot do this line search. Right, so we had called this function g of alpha, right, because x and d are fixed. So given any direction and x, right? Okay, so what is g of alpha? I'll write it once more. F of x plus alpha d for a given x and d. F is a quadratic function, so I'll just plug this value of x. Okay, I just plugged in the value of a different value of x here. So what will this amount to? So I'm just expanding these terms. So ultimately what do we get? So remember that this g is actually a function of alpha, right? So x and d both are fixed. So as a function of alpha, what do we get? Alpha square half t transpose qd plus alpha times x transpose qd minus p transpose t plus half x transpose qx plus c, right? So this is nice. So g of alpha is also quadratic in alpha, right? Okay, so what do you want to solve? Right, this is what we are interested in solving. Okay, so what would we need? So again, remember that your x and your d, they are fixed. That's for a given x and d, you are constructing this function g of alpha. Right. So one thing is, if I want to say that there is no local minimum, I would want g double dash alpha less than 0, which is saying this term here, the coefficient of alpha square, that better be less than 0. Okay, and let's just come back to the first order condition. So g dash alpha will be what? So again, it's just a 1D function as a function of alpha. So what? How do we compute the derivative? It's just usual derivative, right? There's nothing complicated here. So alpha times t transpose qd plus x transpose qd minus p transpose t, and we want to equate it to 0. Actually, let's just see. Let me not do that. So yeah, I want to characterize when can I not find such an alpha. So if let's see. Right. So I'll use this information. So first obvious observation is, for no local minima to exist for this problem, I will have d transpose qd less than 0. Okay. So if I use this information here, when can I say that this first order necessary condition is not satisfied, meaning g dash alpha is not 0? So what I'm asking is, there shouldn't exist alpha such that g dash alpha is 0. So that means one way to do it would be t transpose qd is 0 and x transpose qd minus p transpose t is not 0, right? One possibility. So maybe if it's not clear, let me write it here. Under what conditions on F will we not be able to do exact line search? Okay, that's the question. So let's do push it out there. So in conclusion, to be unable to do line search, exact line search, we need either T transpose QD less than 0 or T transpose QD 0 and X transpose QD minus P transpose T is not 0. Okay. So this was a case where we wanted to do an exact line search and we were looking for conditions under which we will not be able to find this alpha at all. There could also be situations where we would have a lot of alphas to choose from. So for example, under what conditions G of alpha has infinitely many solutions. So let me maybe number the questions just to avoid confusion. So there are multiple parts. So the second part is where we are looking for conditions on this function f such that this G of alpha has infinitely many solutions, right? So first observation is clearly G dash double dash alpha is greater than or equal to 0, right? Which is saying D transpose QD greater than 0, and of course G dash alpha is 0 for infinitely many alpha. Right, so I'm just writing G dash alpha here. Right, so how do we do that? Right. So I'm just trying to bring out this fact that This is of course a very artificial example, but exact line search may not always be possible. So we saw that even in case of quadratic function, depending on what the direction you have chosen, what the matrix Q is, what the vector B is, depends on their numerical values and how the inner products behave. Consequently, that will tell us whether we can do an exact line search or not. So of course we would want to do that, but sometimes given the system of equations you have, you can't. So you have to find different ways of then solving that optimization problem. You have to settle for inexact line search. Okay, right. So maybe let me do one more question along these lines. Should I call it a subpart of that? Yes, I think I will. Okay. Yeah, so it's a slightly complicated situation. So it's still the same quadratic objective function. The way we are choosing the direction is a bit more complicated. So as you'll see, so here, so let me define some vectors. Let's call A as these different step sizes, alpha 1 to alpha q. U is a matrix with column u1 to uq, and we'll change the notation a bit, call this function h of a, which is nothing but f of x plus u times a. Okay, so it is a linear combination of, so imagine that each of these imagine each of these is a direction weighted by some appropriate step size alpha j for each uj, and then that resultant direction is along which you are moving. Okay, you want to find what should be those appropriate step sizes in each of those directions ujes. Okay, and what else are we given? Let's see. Okay, I hope you can still hear me. Alright, so we'll just make one more note, which is that this set of vectors vi I equals to 1 to p is a set of largest possible number of linearly independent vectors such that qvi equals to 0. So this is just a long way of saying vi spans null space of Q, right? And what we are given is ui are orthogonal to these vj's, to these null space vectors of Q. Okay, so obviously this means Qi is not 0 for I equals to 1 to P. Okay, so define these U's such that they don't align the null space, otherwise it's just pointless, as you'll see, because the way we are you just see in the algebra why we need to make this assumption. Otherwise you'll just end up roaming onto the null space of Q, and that's going to result into 0 vectors, and you'll not get anything interesting there. So okay, so let's just write out HA, f of x plus UA is nothing but half of x plus UA transpose. So remember, the objective function is still the same. Okay, all that we have changed is the direction, the D. So again, I am just writing down the algebra, just expanding out all the terms. Right, so I hope it's good so far. So remember that instead of a scalar, now you have a vector A, of which your h is a function. So previously we had g of alpha, now we have g of A, if you will. I'm just using a slightly different notation for convenience. And so instead of alpha scalar, we have a vector A. We want to find that vector A such that we minimize h of A. So anyway, I'll just go ahead with this algebra. So we want to remember, we are given x, we are given u. What we want to find is these a's, a here, a here, a here, a here. That's the argument. Rest all our constants. So as a function of a, we, as you might have suspected, we are going to get a quadratic again. Right, so here we'll have to be careful. It's the argument is a vector, so it's with the, instead of the usual double derivative, we'll have a Hessian here, and as you can see from the expression here, the Hessian is going to be u transpose qu. Okay. So I still haven't really asked the question, what are you trying to look for, but just bear with me for a bit. We'll have to simplify these expressions a bit more using the information we have, and then we'll just, with the question, as you might expect, it's going to be under what cases we'll be able to find a local minimum, under what cases we'll not be able to find a local minimum for this exact line search. The question is still the same, but we will do a few more simplifications. So bear with me on that. So let So what I'm saying is corresponding to the null space corresponding to these m1 to mq, the eigenvalues are non-zero, and corresponding to n1 to np, the eigenvalues are zero. Okay, so I'm just denoting them slightly differently. It will become clear why. Okay, so note that since v1 to vp is the largest possible Li set spanning the null space of Q, dimension obviously, as you can guess it, of null space of Q is going to be P, and hence the number of eigenvectors with zero eigenvalue is P. Right, so I'll just simplify with the help of this matrix. So I'll just set up some notation. I'll just collect these eigenvectors into a matrix, just stack them as columns like this, side by side, m1 to mq, n1 to np, and let me collect the eigenvalues as a diagonal matrix. So what will be Q? Q is a symmetric matrix. So by eigenvalue decomposition, what can I write? As you might have suspected, right, so all that I'm doing is I'm rewriting Q as V lambda V transpose. That's my eigenvalue decomposition. So these are the eigenvectors, and this contains the eigenvalues as a diagonal matrix. So I've just used the eigenvalue decomposition. And why? Because Q is symmetric. Right, so what will this be? MD and transpose, you can just treat them as vectors, and you can just do this. These are just a simple matrix vector products. Right, and note that u1 to uq are orthogonal to the null space vectors. We have span of u1 to uq, nothing but orthogonal complements of this null space of Q, which is span orthogonal complement of span of v1 to vp, and this is orthogonal complement of span of the n1 to np vectors. Because eigenvectors with zero eigenvalue spans the null space of Q. Right? So basically, when we know that the orthogonal complement of the span of these eigenvectors with zero value, that's nothing but the span of the remaining eigenvectors, which is m1 to mq. Right, so every ui can be represented using m1 to mq, right? Because what we have seen is the span of this u1 to uq is nothing but the same as the span of m1 to mq. So what can we write? U equals to m theta for some theta, right? So what was the Hessian? If you recall, it was nothing but u transpose qu, and if I just substitute this m theta here, and the fact that q is md m transpose, because these m matrices, they are orthogonal matrices. So what can I say? So what's the question now? Should I put the 3 here? Yes. Okay, so coming back to the question, so now that I've simplified the problem a bit, under what condition can we do exact line search? That is specifically strong local minimum. When can I get that? The Hessian has to be strictly positive definite, right? So again, I'm just continuing with the algebra that we've already done. So this is true, and all lambda to lambda lambda 1 to lambda q greater than 0. So this is possible when non-zero eigenvalues of q are positive. Right, similarly, so let me write A, B. So for no minimum, it will suffice to say there exists some y such that y transpose Hessian y less than 0. That is theta y transpose t theta y less than 0. This implies at least one non-zero eigenvalue of q should be negative. right? Because this is a diagonal matrix containing all the non-zero eigenvalues of Q. So yeah. So if we try to do a line search for such directions, then again, if the Hessian does not satisfy these conditions, then we may or may not get to that appropriate alpha that we are looking for. Let me switch gears a little bit. Convex functions I should write. So there's a definition of convex functions that was not covered in the lecture. So I thought I'll do that because it's quite often useful. The basic premise is that if there's a convex function, at any point, the line is going to be an underestimator for this convex function f. Let's call this line L. You have this function f, convex function f. You can always draw a line that just supports this, sits below this function. Okay. So what is the definition, by the way, for a convex function f? Or rather, let me write it like this: a function f is convex in X if and only if, I'll just treat with single argument. So function f is convex if and only if f of f of y is greater than equal to f of x plus y minus x transpose gradient f of x. For all x, y in domain of f. Right, so how do you prove this? So we'll assume that f is continuously differentiable. So how do we proceed with this? I hope you can still hear me. So we'll proceed with what we are given, which is to say f is convex. So we'll go this way. So what we are given is of dy plus 1 minus dx less than equal to t of y plus 1 minus t f of x. Of course, t belongs to 0, 1. And for reasons which will become clear a bit later, we'll just take for now excluding 0, 1. So what do we have? F of x plus ty minus x less than equal to t f of y minus f of x. Okay, so all that I've done is kept this term on this side as it is, and oh sorry, my bad, I think I forgot to write a term. Okay, what I meant to write was minus f of x. So I'll just take this term this side and leave the remaining terms here. Okay, so this is what I have, and so one reason you see I'll be taking the t here, and you might anticipate what's coming here. I'm going to take limits and form derivatives here, introduce derivatives here, and for that I would need things to be well defined. Right. So what can I do? I'll take limit t tends to 0. There's no t term on the right side, so there's no change. Now, just for simplicity, again I'm going to resort to the 1D functions, the GTs. So f of x plus t y minus x for a given y and x, I will call that g of t, function of t. So what I have is limit t tends to 0, g of t minus g of 0, right? Because if you put t equals to 0 here, you just get f of x, which is nothing but g of 0. So this by definition we know that is g dash 0, right? And what is g dash 0? It's nothing but y minus x transpose gradient of x plus t y minus x. So at t equals to 0, which is nothing but y minus x transpose gradient f of x. So what do we get? Gradient f of x transpose y minus x less than f of y minus f of x. Okay, similarly you can interchange x and y, and what you can get is is that fine? Okay, so the other side I'll cheat a bit for now. I'm going to assume that f is twice continuously differentiable, because that's going to be simplify the proof a lot. Okay, I leave the other case as an exercise, and if you have any doubts you can just let me know. Because f of y equals to f of x plus y minus x transpose gradient f of x plus y minus x transpose gradient f, so not the gradient, so Hessian, sorry, Hessian f z y minus x, where plus theta x plus 1 minus theta y for some theta between 0 and 1 excluding 0 and 1. By this is the mean value theorem, second order mean value theorem. And there's another characterization which I'm going to rely on here, which is that Hessian is, so fx convex if and only if f is strictly positive semi-definite. Right, so I'm just going to use that, because then this quantity is going to be greater than or equal to 0, hence f of y is greater than or equal to the thing that we just proved. Okay, I am messing up things. Okay, yeah, sorry, I got mixed up. I want to go the other way around. So I'm given, sorry about that. So I'm given that f of y greater than or equal to f of x plus y minus x transpose gradient of f of x. Therefore 3 becomes, so I take this thing on the left hand side, which will be greater than or equal to 0. Right. So I just leave it to you, just fill in the rest of the steps. I mean, there is one more line left. So yeah, you could go either way and you could end up basically proving the convexity of this. So let me just complete the argument actually, since I'm already here. I have used the fact that Hessian is this. What does that tell me? Let's see, this is not conclusive, so I thought I'll get something here, but if f is, I'm using second order mean value theorem, using the fact that I have the first order characterization, I think this is fine. So this is going to be true for all x, y. There is some shortcut that I'm taking here, because there is a fixed z here which depends on the x and y I pick. So it's not like I am getting, but it's fine. I mean, you could have some small order terms here. It's norm of y minus x, and these terms will go to 0 the moment you are in the vicinity of, let's say, if x is a point of interest, x star, let's say, and then y is your iterate, and if you're close enough to x star, then those higher order terms are negligible and you're pretty much close there at that point. So then the Hessian is positive semi-definite, and this is if and only if f is convex. So I have shifted the burden to something else slightly, which is to say that f is convex if and only if the Hessian is positive semi-definite. But I think that's all that's coming to my mind. So just try this out. So this proof then now hinges on the fact that, okay, how do I prove this Hessian being positive definite is equal to f being convex? You know it's true, but how to go about proving it? So since we are not having much time, I am going to move on to one more question. So sorry for keeping the argument incomplete. But if you have any doubts, yeah, please reach out to me regarding the remainder of the proof. Okay, so one more question. Since we are on the topic of convexity, so I'll probably wrap up this course and the discussion, everything with this one more question. So nice bit of algebra involved in this. So the question is, prove or check the convexity of f of x is log of e to the x1 e to the xn. So x is a vector, n-dimensional vector, right? Log of sum of exponentials. So what do we do? So what's the convexity? How do we check the convexity? So one way to do it, that's what we are going to check here. Check. So we will check if the Hessian is positive semi-definite. That's what you're going to check. So this will require us to then compute the gradient and then the Hessian. So how do we go about that? So we'll just do what we discussed just now, which is compute the gradient first. Computing the gradient is easy because I'm taking del f of x by del x1, del f of x by del xn, which is nothing but e to the x1 by e to the x1 plus e to the xn. Similarly for each of the components, to the xn, e to the x1 plus e to the xn, right? That was easy, but seems complicated now that you have to compute the next set of derivatives. So what we now want is two things: del 2f x del x I squared right. So how do we do that? So what is this? Del f of x by del xi, take the partial derivative of that with respect to xi. So here we have the ith term, which basically looks like this: e to the xi by summation of the e to the xi xj's. Take the partial derivative of that with respect to xi. So del by del xi e to the xi summation j e to the xj. So how do we do that? Summation j e to the xj e to the xi minus e to the xi times e to the xi, because the partial derivative of this with respect to this is going to be just that term, and summation j e to the xj whole squared. Right, so similarly del 2 fx del xi xj, which is nothing but this, and we are going to proceed in the similar fashion. Right, so what is it going to be? So here note that j is not I, right? Otherwise we've already computed that expression here. So we are going to have, so that the partial derivative of this with respect to this is going to be 0 because j is not I. So we will only be getting a non-zero term from this when you take a partial derivative of this term, the denominator. Okay, so what do we have? What is the Hessian? Let me write it down. So the diagonal entries, so the diagonal entries are going to be these, the non-diagonal entries are going to be this. Right, so the diagonal entries for each I, they look like this, and the non-diagonal entries look like this. So let's just write it down. So e to the x1, e to the summation k e to the xk minus e to the x1 e to the x1 e to the minus x1 e to the x2 e to the minus e to the x1 e to the xn. I'll just keep on filling these things. So there's a common thing which is the denominator term, summation e k squared, so I'll just take that out. So in each of the terms there is a denominator term that is common, so I'll just take that out and put it here outside the matrix. And so remember that when you take I, if you interchange I and j, it's going to give the same expression, right? Here it doesn't matter what order you take the partial derivatives. In general it's not true, but here it is true that del 2f by del 2f del xi del xj is the same as del 2f del xj del xi. So whatever terms we see here, they are going to reflect. So basically around the diagonals, the terms are going to be reflected. The same values are going to come. Okay, so I'll just I'll just keep filling that for each of the rows. Okay, so this is my diagonal term, first diagonal term, this is my second diagonal term, and then so on, and then I'll get right? So rest of them are non-diagonal terms. Now the expression looks a bit ugly, but we can simplify it. So I'll just keep the scalar here, and the matrix can be split into these two parts. So you notice this one thing, these xi xj terms that you're seeing as negatives, the same terms are appearing here. Okay, so that's going to simplify matters a lot. So we can just first look at these diagonal entries. Let me just write it down so that it's less confusing. So all these terms, we have just brought them as a this term, so as this matrix, and these first terms of the diagonals, you just written them as a separate diagonal matrix. And this is nice because then this thing gets cancelled out with one of these terms. That is just a simple diagonal matrix. And this one can be written as a rank 1 matrix in a nice outer product form. So what we'll end up getting is where is it? Okay. I don't even need to do that simplification. I can just directly compute what I really want, which is that I want this quantity, the Hessian y transpose Hessian times y, to be non-negative. I want to see if that happens or not. So so what's the expression? So remember that this is a diagonal matrix. When I do a pre and post multiplication with this y transpose and y, it's just a summation of these entries, product of each of these term-wise product, and then just add them up. So I'll have to be a bit careful. There are multiple indices, but it's basically and remember this thing, it's nothing but e to the x e to the xn times e to the x1 e to the xn. It's just an outer product. So if you call this vector a, it is nothing but a transpose. That's all it is. Okay, let's verify it here. So y transpose e to the x1 e to the x2 e to the xn e to the x1 to e to the xn y, and there's a reason for why I'm writing it like this before, rather than simplifying the matrix and then proceeding ahead with the calculation. Can use Cauchy-Schwarz, as you'll soon see. So this can be compactly written as the following: yi e to the xi by 2 whole squared, and summation k goes to 1 to n e to the xk by 2 whole squared, minus summation I yi e to the xi this whole thing squared. So let me write a vector u, which is nothing but y1 e to the x1 by 2, yn e to the xn by 2, and v as e to the x1 by 2, e to the xn by 2. So what does this thing turn out to be? Some positive quantity times summation I equals to n ui square vi square minus summation I equals to 1 to n ui vi whole squared. What is this? Sorry, I made a mistake here. I meant to write two summations. So what is this? Cauchy-Schwarz, right? So we have gotten that y transpose Hessian y is greater than equal to 0 for all xy. For all y, and this is true for all x in domain of f. Therefore f is convex, and we are done. So I already overshot, so we'll stop here. Thank you so much for coming to the discussions. If you have any doubts, please don't hesitate to reach out. Thanks for coming.